myclass.com.
Our new topic, asymptotic analysis. What is asymptotic analysis? Asymptotic analysis refers to computing the running time of any operation in mathematical unit of computation. We can express a running time of an operation in a mathematical function, in the form of a mathematical function. So, in terms of algorithm, asymptotic analysis refers to defining that mathematical boundation of its runtime performance based on the input size. What is the actual size of the input? Based on that, we can bound that runtime performance, the maximum time and the minimum time, in terms of a mathematical function, and we can call it as a mathematical boundation. Such type of analysis, we can say that this is asymptotic analysis. Usually, the time required by an algorithm falls under three types. What are they? Best case, average case and worst case. Best case means, the name itself, it says minimum time required for program execution. Very small time or minimum time that is required for program execution to complete the execution and to get the desired output. Worst case means the opposite. That means the maximum time, how worse it will perform. The maximum time required for program execution. So the average time or average case means average time required for program execution. These three terms are very important. The best case, average case and the worst case. What are the asymptotic notations? Three basic notations are the big O notation, omega notation and theta notation. What is big O notation? The notation big O or order of n or big O of n is the formal way to express the upper bound of an algorithm's running time. Upper bound means worst case, the maximum time it will take. It measures the worst case time complexity or the longest amount of time an algorithm can possibly take to complete. Let's take f of n as our example. We can express the running time of an algorithm in terms of a mathematical function, that is f of n. In the big O notation case, we have to find a g of n and we can bound the f of n into the g of n function. Let's check. We can say that big O of g of n, f of n equal to big O of g of n, there exist positive constants c1 and n0 such that 0 less than or equal to f of n less than or equal to c into g of n for all n greater than or equal to n0. Suppose f1 is our function that express our time complexity and g of n is another function and c is a constant. So when we can find a number n0 such that n greater than or equal to n0. On the right of n0, this the value of f of n is always falls under c into g of n. This is our input direction and this is the time. Okay. So the f1 grows is like after n0, after the value of n0, f of n is always under c into g of n. So we want to find the value of c also. So the positive constant c and n0 such that f of n is less than or equal to c into g of n. Let's check. We can say it like f of n equal to big O of g of n if there are positive constants n0 and c such that to the right of n0 the f of n always lies on or below c into g of n. Let's take an example. In this, our function f of n equal to 2n plus 3. That means our algorithm takes the time as a 2n plus 3 when the value of n is the input size. So the time function of a particular algorithm is 2n plus 3. So we want to bound this 2n plus 3 to another function. Let's take, we can say that g of n equal to n. Let's take one example, g of n equal to n. So we want to find a constant. So a particular time c into n is greater than or equal to our f of n. So in the case we can say that, let's see, here input size is starting from 1. So n equal to 1, the minimum value is 2 into 1 plus 3, 5. So we can find that c equal to 5 for our c into n. That means when n equal to 1, 2 into 1 plus 3, that equal to 5. Our constant is 5 and the value of n is 1. So here we can write like 5 is less than or equal to 5. We can say that f of n is big of g of n. For a constant value c equal to 5 and from n equal to 1 onwards, f of n is always under c into g of n. Okay. Hence, when we can find such function, we can write like f of n equal to big of g of n. That is the maximum time or the worst case of an algorithm should take. Clear? Next, notation, omega notation. The notation omega of n is the formal way to express the lower bound of an algorithm's running time. It measures the best case time complexity. The minimum time taken by an algorithm to get the output, or the best amount of time an algorithm can possibly take to complete. So that means we want to bound this our algorithm function to another function to notate with omega. So here our function is f of n and we want to calculate two positive constants c and n0 such that to the right of the n0 the f of n is always falls above c into g of n. So the omega of g of n equal to f of n, there exists positive constant c and n0 such that f of n is greater than or equal to c into g of n for all n greater than or equal to n0. To the right of the n0, f of n is always above the c of n, c into g of n. So we want to find the very next function that is very closer to f of n. Lots of functions are, we can find the lots of functions that is always lesser than f of n. But we want to find the very next function that is very closer to f of n. That is the lower bound of an algorithm running time. So the omega notations means f of n equal to omega of g of n if there are positive constants n0 and c such that to the right of n0 f of n always lies on or above c into g of n. Let's take the same example. Our f of n equal to 2n plus 3. Our g of n equal to n. The n is starting from 1. Let's check when c equal to 1. When c equal to 1, 2 into 1 plus 3, that means 5. Here 1 into 1 equal to 1. So this is true. That means f of n is greater than or equal to c into g of n. We can say that, we can write like that, f of n is omega of g of n. It means that for a positive constant c and n0, the right of the n0 f of n is always greater than or equal to c into g of n. Clear? Next, our notation, theta notation. The notation theta of n is the formal way to express both the lower bound and the upper bound. That means the average case of an algorithm's running time. How it's represent? Theta of g of n equal to f of n. There exist positive constants c1 and c2 and n0 such that 0 less than or equal to c1 into g of n less than or equal to f of n less than or equal to c into g of n for all n greater than or equal to n0. So this is our input direction and input value, and this is for time. We can find a value n0 and two constants c1 and c2 such that for the same function g of n, we can say that f of ns lies between c2 into g of n and the c1 into g of n. Let's take an example. Here, f of n is equal to theta of g of n if there are positive constants n0, c1 and c2 such that to the right of the n0, the f of n always lies on or above c1 into g of n and on or below c2 into g of n. We have already found that 2n plus 3 and for our f of n 2n plus 3 and g of n n. This g of n is, we can write like f of n, we can write like big of g of n, and f of n is also omega of g of n. That means we can bound f of n between c1 into g of n and c2 in g of n. In this, we take our example as f of n equal to 2n plus 3 and g of n equal to n. So we want to calculate c1, c2 and an n0 value. We have already found that f of n is bound with the g of n for lower bound and the upper bound with the two different constants. For our value for our upper bound c2, our constant is c2 equal to 5 and n equal to 1. That means 2n plus 3. 2n plus 3 equal to 5. 2 into 1 plus 3, 5. 5 into n. It means we can write like 5 is less than or equal to 5 into n. 5 into 1, that means 5. N equal to 1, that the n0 value is 1. From the value of n0, that means n0 when n equal to 2 means 2 into 2 plus 3. 2 into 2 plus 3 means 7 and 5 into 2 is 10. So here also it is true. So from this value onwards, f of n is always less than or equal to c into g of n. And for the value of c1 equal to 1 and n equal to 1, 2n plus 3, 5, and that is greater than or equal to our 1 into 1, c into 1. So from 1 onwards, 2, 3, 4 like that, f of n is always greater than or equal to c1 into g of n. Here c2 into g of n. So we can bound up to the upper limit and the lower limits. Hence, we can write like f of n is theta of g of n. Clear? That's all about our three basic notations. Big O, omega and theta notations for analyzing an algorithm in terms of a mathematical function. Thank you.